Reload.
Yes.
11 o'clock, Sunday morning, the fifth Sunday of the month. It's time for a special chai and wine, up close with science, where we are live from a lab at the IFR. So if you're joining us on YouTube, good morning and welcome from the Crystal Growth Lab at the IFR, the Tata Institute of Fundamental Research in Mumbai, where we are with Professor Tamilavel, who has set up one of the most wonderful facilities for crystal growth in India. You've heard of crystals, sugar crystals, salt crystals, ice crystals, perhaps. But crystals are at the heart of a lot of science, especially physics. And in this lab, Professor Tamilavel and his group grow a lot of very interesting single crystalline materials that they're going to show us today and talk about. And along with him, we have a lot of other people in the lab. There's Ruta to help us with some of the growth. There is going to be Gaurav and other students who are around who will show some things in the lab as well. Professor Tamilavel, he did his PhD many, many years ago from Anna University in Chennai, spent many years at Osaka University learning some very high-tech crystal growth techniques, and about 17 years ago came back here and started this crystal growth lab, which has now grown to encompass several ways of growing crystals, and he'll be talking to us about that. So over to you, Tamilavel. What do we have here?
Thank you, Arnav. I welcome you all to the Crystal Growth Lab. To start with, I wanted to show you something interesting. We have a optical floating zone furnace, which is here, which employs this lamps. It's halogen lamp. So it is a 1500 watts lamp. And during your childhood days, many of you might have played with this sun's rays focusing onto your particular paper and burning the paper. So it employs a similar function here. And then we can grow single crystals out of this instrument. So in this instrument, we can heat up to 2000 degrees centigrade. The sample whose melting point is as high as 2000 degrees centigrade can be melted in this furnace, and we can grow the single crystals. So right now, you can see these lamps are there, and there is a concave mirror. This concave mirror focuses the light onto a particular point here, and you can see the sample which are mounted here. So this is a feed rod, and this is the seed material. The material to be crystallized is hung from the top, and this is the seed material which is at the bottom. So to start with, we will melt the tip of these samples, and then we will attach them together, and we will try to grow the crystal. So you are going to see this live in action in few minutes of time. Just before that, we need to start this instrument. So this will take roughly some 20 to 25 minutes to reach the maximum temperature. So my scientific officer, Ms. Ruta Kulkarni, will start this process. In the meantime, I will take you around our laboratory to show you the various other facilities that we have. Okay, so as Arnab has already pointed out, crystals are the pillars of modern technology. That means crystals are there everywhere.
And I'm just going to say that we can't hear you, so please put your questions and comments in the chat, and we will reply to them.
And the crystal growth is a branch of science which has 3 different flavors. It is art, it is science, and it is technology. It's art because you need to have some experience and expertise in growing a single crystal. It's not that you buy a crystal growth furnace or crystal growth instrument, it will produce a crystal for you. It's not like that. There are many instruments where you buy something for some purpose, and you get the data out of it, and you get analysis, you do the analysis. But unlike those instruments, crystal growth is an art. That means you need to learn that, and you need to have some experience, and you gain the expertise, and you can grow high quality single crystals. So it is an art, and it is a science, because you need to know the melting point of the sample, you need to know the solubility, you need to know the vapor pressure and all these things. So it's a science as well, and it's a technology. Huge crystals can be grown by melt growth techniques. One of the techniques which I am going to explain you a little later is Czochralski technique, which is a very popular technique to grow bigger size crystals. And these days, solar energy is used everywhere. And to grow large size single crystals as a substrate material for solar cells, it's very important. And you can consider this as a technology. So if you are interested in becoming an entrepreneur, you can take crystal growth as your specialization field, and you can master crystal growth, and you can grow large size single crystals. So that's the need of the hour right now. So right now I am going to take you around my lab. I'm going to take you to I'm going to show you a furnace where we can melt samples whose melting point are as high as 3000 degrees centigrade. So this is one of the furnaces that we use to grow the crystals, and this is called a tetra arc furnace. So the basic idea is that it has a tungsten electrode. There are 4 tungsten electrodes, 1, 2, 3, and 4. And here we can melt samples whose melting point are as high as 3000 degrees, close to 3000 degrees centigrade. So if you can show that inside, that will be good. So this is a tetra arc furnace. As you can see, there are 4 electrodes inside, and there are materials which are kept to melt, and these materials are kept inside on a copper hearth. That means there is a small holder to
that bottom portion is
hearth. So
and the 4 needles that we see are electrodes.
The tungsten electrode.
Okay.
So we can pass current as high as 100 amperes to these tungsten electrodes, and we can melt. But to start with, we are not passing 100 amperes. We will strike the arc with 10 amperes of current. And since this is a metal, by striking an arc with a higher current of about 10 amperes, an arc will produce, and that will melt your sample. So we are going to see this live in action right now.
But Professor, it looks like it's some closed chamber.
Yes.
So why is it a closed chamber?
See, because metals get oxidized at elevated temperature.
Okay.
So if you heat it up in open air, all metal will get it will absorb oxygen, and it will get oxidized, and eventually you will get the oxide of that metal. To avoid that oxidation, we are keeping everything inside this vacuum chamber. So right now, this is a vacuum chamber where we have pumped it down to 10 power minus 6 star. And it's not possible to strike an electric arc in vacuum. So that means to strike an electric arc, we need to have some medium. So we have isolated the chamber after pumping it to 10 power minus 6 star, and we have filled it with argon gas. Argon being inert, it will not react with your material that we are going to melt right now. So right now you can show that this is the chamber pressure as of now. It is filled with argon gas right now here. It is under a partial pressure of argon gas. The reason for this partial pressure is that if you put at atmospheric pressure or little excess atmospheric pressure, when we heat up these metals, the gases comes out of these metals. So, and also the argon which is there inside, it gets expanded. So to avoid the excess pressure, we are putting it into a little bit of partial pressure of argon gas. So right now, the material is, we have 3 metals in that. So we are going to make a alloy of these 3 metals.
So those pieces on the earth is the charge to be melted.
Yes. We have cerium metal, we have rhenium metal, we have silicon in that. So there are 3 metals which are kept on the copper hearth, and this copper hearth is water cooled. So cerium
metals again?
Cerium.
CE.
CE.
Okay.
Cerium melts at around 800 degrees centigrade. Rhenium, it melts at around 3200 degrees centigrade. Silicon, it melts at around 4400 degrees centigrade. So we have 3 different melting metals: cerium, rhenium, and silicon. So these are taken in the ratio 1:4:2, 1:4:2. Cerium is at 1 mole percent, and 4 mole percent of rhenium, and 2 mole percent of silicon. That is the composition that we are going to melt it today.
And will it form cerium, rhenium, 4,
silicon 2, or it will form some other thing which we will find out?
So in this case, there are literature available that it forms 142, cerium, rhenium 4, silicon 2. So definitely it will form in that particular composition. So right now, now there is a question that you may ask. Copper has a melting point around 1000 degrees centigrade. 1100 is the melting point of copper, but rhenium has 3000 degrees centigrade melting point. So whether this copper will react with your rhenium or not. The advantage of using copper hearth is that the copper hearth is water cooled and it has a high thermal conductivity. So the most of the heat that is produced in that during melting is taken away by this copper hearth, since copper has a high thermal conductivity. So the copper will not react with these things. Only these three elements will melt, and any metal, when it is in its molten state, when it is in liquid state, will react with the other metal and it will form a compound. So you can see this huge exothermic reaction that is happening right now. So
would it also mean that it's difficult to make copper in this furnace?
Yes. So melting copper in this furnace is relatively difficult because the copper hearth is water cooled, and whatever the electric arc that is hit on the copper material will be transferred and to the water that is being because of the high thermal conductivity of copper. So let's see how this sample now, how this is being melted right now. So you can show this.
What are these tubings on top? Also, there is some motor-like thing.
Yeah, this is for growing a crystal. Actually, this is a crystal growth instrument. Right now, we are not going to grow any crystal out of this. We are going to do the preliminary melting of the material that we wanted to crystallize at a later time. So before we do the crystallization process, we need to melt the samples repeatedly, some 3-4 times to make it homogeneous. So right now, this homogenization process is being done. Okay. So
it could be a multi-step process.
Yeah, it's a multi-step.
It cannot be like one can put the interesting materials inside and get a.
Now, for that, we need to set up the things. We need to put the seed crystal. Right now, there is no seed crystal there. We are just going to melt the sample and we are going to show you how an alloy is formed. Okay. Whereas in the other furnace, just now I demonstrated there in the optical floating zone furnace, we are going to see live in action about how we are growing the crystal using the optical floating zone, because there everything is set up. We have a seed rod, we have a feed rod, and then we are going to melt the seed and feed rods, and we are going to attach the seed and feed rods. So you will see in action how the crystal is grown. Okay, so let's get going from here. So right now you cannot show this directly because when I strike the arc, it will be a powerful light. So we need to put some polarized filters here so that you don't see the complete light there.
So this dark glass is for that?
Yeah, it is for that. So right now I'm going to strike the arc. You can show there. So this is the electric arc. We have 4 electrodes. Right now I have struck on one of the electrodes, and you can see this red color flame is because of the material, cerium. You can put that a little bit down. That's this electrode. So now I'm striking the electrode number 3. So the small balls which are seen here is the rhenium balls, and the cerium has already melted. Now the cerium is reacting with rhenium, and then it is also reacting with silicon. So the melting point of rhenium is 3000 degrees. You can see that it is getting melted. And we can rotate the sample so that it melts homogeneously. So one of the rhenium balls has is little bit outside the melt. So maybe it is difficult to melt it right now. The second melt, we can put it closer and we can melt it. So this melting process has to be done for 2 to 3 times so that everything, the sample gets completely melted. So this is the rhenium ball whose melting point is around 3200 degrees centigrade. Right now, you are seeing the rhenium, which is in molten state, which is at 3000 degrees centigrade right now. And the other big melt is that it has melted with part of the cerium, rhenium, and silicon. Only a small rhenium ball is left, which is unreacted. Maybe in the second melt, after we open the chamber and we put it upside down, and we can melt it again so that everything becomes a homogeneous alloy. So this heart can be rotated. Now it has reacted with that entire thing. Now the sample has completely melted. So once, because of the surface tension, it takes up a proper shape, like a ball. The sample is getting melted completely now. Argon gas. It is an inert gas, so it doesn't react with your melt. So without that, we cannot strike the arc. So we cannot strike the arc in vacuum. So to strike the arc, we need a medium. So that is argon gas. Of course, you can use helium. Helium is a little bit expensive. So, but here argon is generally preferred. Yes, yes, yes. So right now, I'm going to stop these electric arcs one by one, so that now, and I will open the chamber and I will show you how it looks like. So right now the melting is done. So we need to do this melting process some 2 to 3 times so that the entire alloy becomes completely homogeneous. So right now I ask my student to open the chamber. So before opening the chamber, we should make sure that the pressure is at atmospheric pressure. Right now it's at partial pressure of argon. That means it's under vacuum. So we have to fill the gas up to the atmospheric pressure, and then we will open this chamber right now, so that you can see how the molten alloy looks like.
And this is all controlled from.
Yeah, the electric arc control is, everything is controlled by this controller. And this controller is little bit sophisticated in the sense that we have a seed rod which is coming from the center. This is to grow the crystal by Socrates method.
Can we see the seed rod?
We cannot see that because the entire bellow covers the seed rod. But once I open the chamber, maybe we can have a look at it. So there is a possibility to see the seed rod there inside. So this method of crystal growth is called Czochralski method. Czochralski method is quite interesting. A lot of big size crystals can be grown by this method. And there is a story behind this Czochralski method. So by the time he opens up the chamber, I will tell you the story. See, this Czochralski method is discovered by a scientist named Jan Czochralski. He's from Poland. He went to do his undergraduation in Germany, and he was studying the solidification of metals, low melting metals, like for example, bismuth, tin. These metals have very low melting point, less than 400 degrees centigrade. So he used to melt these metals and then solidify it. You can open the chamber in the meantime. So this he used to solidify. He used to melt these metals and then rapidly solidify these molten solution. And then he wanted to see the microstructure of this material. So in those days, there are no fountain pens. This was in 1911. So he used to take a note by dipping his pen in the ink pot, and then he writes down his note in those days. So once, instead of putting his fountain pen inside the ink bottle, mistakenly, he put it into that small crucible, which contains the molten tin or molten bismuth, molten tin, I believe. So then he realized his mistake. He took his pen very rapidly out of the melt, and he found a string of tin came along with his nib of the pen. Then he realized that. Then he did an X-ray diffraction of this string of tin, and he found that these produce diffraction spots. The small string of tin produced diffraction spots, and then he found that there is a way to grow a crystal. So this is by an accidental discovery. He has discovered this method of crystal growth, which is named after him, which is called Czochralski method. And this is one of its sophisticated furnaces of Czochralski method. So you can see that. So right now you have seen that this is the alloy that we have made as of now. This is the copper hearth. The water comes inside this tube up to this copper hearth. So because of the thermal conductivity of copper, the entire heat is taken by this copper. And we had these cerium, rhenium, and silicon, which are kept as individual metals. And as I told you, those have different melting points. The rhenium being the highest with 3200 degrees centigrade. And we have melted this sample, and this is how the alloy looks like. So right now, this does not have a proper shape. We have to put it upside down, and we have to melt it again. So putting it upside down is important so that the bottom part, which is in contact with the copper hearth, might not have melted properly or might not have mixed with the solution. So we need to put it upside down, and then we have to melt it again. So this process we are going to do right now. In the meantime, I need to clean this copper hearth. So let's go and see the optical floating zone furnace in the meantime. So right now, we are now going to show you about this optical floating zone furnace, where the
what are we seeing here?
As we shown you, three drawn and three drawn. Now I slowly ramped up the lamps. I have ramped up the lamps, and now you can see there were 4 mirrors, so 4 filaments, 4
So
lamps.
this is the video camera that we are seeing.
Yeah, that camera is attached there because we cannot see what is happening inside. So that
too
camera,
bright.
yeah. So the camera has the filter, and we can adjust the intensity and see the growth happening. So as you see now, I have ramped it to 40% of lamp power, and it has started melting. Now once,
There is something here that is turning around.
yeah, this is actually we are growing here oxide single crystals. Like there you have seen in tetrarch furnace, as soon as the arc strikes, the metal starts melting. because metal has a very good thermal conductivity, but oxides do not have good thermal conductivity, and hence we have to rotate the rod and slowly take it to its melting temperature. It takes time to
So
heat up.
you have 4 lamps,
Yeah.
and there are 4
Four
mirrors that is focusing the light
Yeah.
on this point,
On this point.
and it makes it hot.
Yeah.
It's just like how we burn something with a magnifying glass.
Yes, yes.
But you're focusing the light over
Yeah.
here, and you're heating this
Yeah.
rod, and to make it uniform, you're
You are
rotating the
rotating
rod slowly. That's
Yeah.
what you're doing
Yes,
here.
yes.
Okay.
And then
And
you have
can
seen
control
there are
everything
yeah.
on this
on this
camera,
camera.
on this computer.
So,
Sorry.
yeah. And
Okay.
yeah. And you have seen there are 4 lamps. So there are 4 filaments, but since they are focused at single point, you can see here a single filament.
So right now the feed material is melted at the tip. You can see the metal.
So the drop is forming. Once it is totally melted, we can take up the
So
sheet.
you know it is
and
melted because it has curved. It's forming a drop.
It is forming a drop, and you can see some shiny metallic shiny melt here.
So, and what material are you melting?
This is cobalt germanide. Cobalt germanide.
Cobalt, germanium, and oxygen.
Oxygen. Yeah. This is CO2 GeO4.
Cobalt, germanium, and oxygen. So in this furnace, you melt oxide material.
Yes.
So,
Yeah.
So right now, this method of crystal growth is called floating zone method, where the zone, the region which is hot, is not held by any hearth or any crucible or something like that. It is just floating. So that's why it's called a floating zone method. So we can grow oxide crystals using this technique. Right now, I will show you some of the examples. So this is one of the crystals that we have grown. This is gallium oxide material, which is doped with chromium or vanadium. So it gets this green colored gallium oxide. So typically, this is a opaque white colored rod. I don't have that polycrystalline sample, but this is a single crystal. Once you make that as a single crystal, you see this kind of transparent crystal. So this is before growing that crystal. This is how it looks like. After you grow the crystal, the same rod becomes like this green colored because of the doping. Otherwise, if it is undoped, then the gallium oxide will look like this.
It's almost it's very transparent.
It's transparent. It's a single grind. There are no grind boundaries here. Whereas in this case, it is a polycrystalline feed rod, and there are lots of grinds in that. And because of that, there are lots of grind boundaries. And because of the grind boundaries, you don't see the transparency there.
Quite beautiful.
This is quite interesting. But making this rod is not so easy. One has to put a lot of effort to get this kind of lengthy rod. So to make this, my student Manisha, she has made all these rods, and maybe she can explain you how she prepared these rods.
Hi. So,
Just a second, you can use the microphone.
So you're going to tell us how you make these long rods out of powder.
yes, I'll tell you how to make these feed rods. For that, we need to blend the powder in water. So, we have this setup where we have a funnel and a balloon attached with it. So, we fill small amount of powder in the balloon like this. We take small amount of in the spoon and add and tightly pack it with a rod. After you finish packing for the added length, you disconnect it, and like you get some rod like this. This is a smaller diameter balloon we use for some other powder. So after you tightly pack this powder, a balloon with this powder, you connect it to the vacuum pump. the rotary pump. Then you remove from the pump and then you put it in the hydrostatic pressure.
Why do you need to put it in the pump?
You want the rod to be tightly packed, so you want to remove out all the remaining air content in the balloon. So in order to make it again tight, you put it in a hydrostatic pressure gauge where you get you apply pressure from all the directions. Then you want to remove it from the hydrostatic pressure gauge. You get something like this. And this rod, you keep it in the furnace. Then you have to remove the rod from the balloon, and you put it in a furnace and anneal it at high temperature. After that, you get a rod like this, this is hard and densely packed. This you can use as a feed rod for your growth. Yeah,
Let's get back to that. Okay, right now she's about to engage this feed material onto the seed crystal. So once the sample is perfectly melted, you just attach the feed material to the seed like this. Now that it has been engaged, the feed and the seed rods are engaged. Now you can slightly rotate it. The feed material in the clockwise direction and the seed material in the anti-clockwise direction. So if you rotate it, the temperature uniformity will be there. So right now the temperature is too much, so that is why it has dropped. So this is how the crystal growth happens. I mean, sometimes you see these kind of difficulties because the temperature is too much right now. So one has to be very close to the melting point of the sample, but it should not be very high away from the melting point. So right now the problem was that the temperature here was too much. We don't have any means to measure the temperature as of now. So we need to judge from our eyes whether it is exactly at the melting point or just above the melting point and things like that. This comes from our experience. So this is the second time or third time we are attempting this crystal. So we know what is the power of the lamp that we have already applied to this growth. So right now we are keeping very close to that power of the lamp, around 40%. Yeah, we will show you already previously grown recorded video so that we can understand how the crystal growth is happening. So right now the seed and the feed, the feed material is molten from the top. You can see a meniscus, very nice meniscus. Now the bottom one is a seed crystal, which is already grown crystal, which is oriented along a particular crystallographic direction. And right now we are going to engage that. You can see that the top seed material, which is molten, it will be dropped into that seed material. You can see that the melt is engaged right now. Then we employ a rotation. The top is rotated in anti-clockwise direction. The bottom is rotating in the clockwise direction. And you can see that slowly we will pull this down. So the pulling speed depends on material to material. In this case, it's gallium oxide. We have employed a pulling speed of about 15 mm per hour. So the growth happens in about a single day.
Why do you rotate it?
So the rotation is necessary for this kind of oxide materials because the uniformity in the temperature is not achieved here. So to achieve the temperature uniformity and the sample homogeneity, we need to rotate the sample, in this case of oxide materials. Yeah. So right now, just a while ago, I was just explaining you about melting these three metals. This is cerium. This is the cerium metal, and this is how the rhenium looks like. It has a melting point as high as 3200 degrees centigrade, and this is simple silicon. 1400 is the melting point. Now you can see that this is kept inside this what is that? Ziploc cover, Ziploc bag, and this is also kept in Ziploc bag. Whereas this is kept inside a special container, which is in a glass tube. This is kept in vacuum. The reason is that cerium is easy to get oxidized. So in order to avoid the oxidation, although these are metallic samples, if you keep it at open air for about a day or two, it will become completely powder. To avoid that, we are keeping it inside this sealed tube. So As of now, you have seen two different type of crystal growth techniques. One is by melting in a tetrarch furnace, and another one is by doing this floating zone technique. But crystals can also be grown from solution. So if you want to grow a crystal, you should take it to its liquid state. So any solid cannot be just translated into a crystal. You should take it to its liquid state. It's not always the case that you need to take it to its melting point. For example, I can tell you that sodium chloride, the table salt, its melting point is 800 degrees centigrade. So if you want to grow a crystal of sodium chloride, it's not necessary that you should take it to its melting point of 800 degrees centigrade. On the other hand, it can be grown at room temperature by dissolving it in water. So the point which I wanted to make it is that it's not always the case to take it to the melting point of the sample to grow a crystal. So, like for example, in the case of sodium chloride, you know that sodium chloride dissolves in water. So let us say in 100 ml of water, about 10 or 11 grams of sodium chloride can dissolve. So you can visualize that you take 100 ml of water, you can add 10 grams of sodium chloride to that and keep stirring it. Then the sodium chloride will dissolve in that. When you put, let us say that in 100 grams, 10 grams of sodium chloride dissolves. When you put the 11th gram of sodium chloride, it will not dissolve anything further. That means the solution has become saturated. So more sodium chloride will not dissolve in that 100 ml of water. So now you have a saturated solution. You heat the solution from room temperature, let us say 25 degrees centigrade to 40 degrees centigrade. Then now you can add more sodium chloride to the solution. Let us say that you can add 5 more grams of sodium chloride to that 40 degrees centigrade solution. When you put the 6th gram, that means the 16th gram, when you put it, it will not dissolve further because the solution has become again saturated. So this second time saturation state is called supersaturation. So this supersaturation state is necessary to grow a crystal from solution. So this is one of the very simplest techniques. Anybody who listens to this talk can easily grow this crystal in their home. Like all that you need to have is that you need to have some hot water, dissolve a sugar or salt solution, and allow it to cool down. You can see that the second day or the third day, you can see some crystallization of sugar or salt. You can right now I can explain you with a demonstration of copper sulfate. This is a copper sulfate solution which has a high solubility in water. Let us say that this is about 200 ml of water. Some 20 grams of copper sulfate has already dissolved in it. And when you leave the solution as it is.
On YouTube, I don't know why. Just hang on. Is any other mic on? There is some echo.
Is this microphone on or? So there is some technical issue. Yeah. So right now, this copper sulfate solution, I was just explaining to you. So if you leave the supersaturated solution for about a day or two, you can have these kind of crystals which are growing at the bottom of this crucible, this beaker. You can see lots of tiny crystals. When you leave it for second or third day, you can see that these kind of small crystals that grow inside this So you can see these kind of small tiny crystals that is settled at the bottom of this beaker of a supersaturated solution. So that means the solution was heated to 50 degrees centigrade. We have added more copper sulfate and I have brought a supersaturated solution. We allowed it to cool down to room temperature. Then you get these kind of tiny crystals inside this beaker. And then you take one of these crystals and tie them as a seed crystal and prepare another supersaturated solution and put it inside the solution. So here, when you dip it inside the solution and allow it to leave the solution undisturbed for about 1 day or 2 days, then you can see that the crystal is growing. So to achieve this, you can see that this kind of this is a multiple nucleation that has happened, and there are many crystals. And this is a unique crystal that has been grown. This is a large size copper sulfate crystal, and I will say that this is large size compared to this other small crystals, but you can grow a huge, relatively very big crystal that you can grow by this solution growth technique. So this is how one can grow these kind of water soluble materials. But in our lab, we are not growing crystals that are soluble in water. We are working with metallic systems. We are working with oxide systems, which are relatively difficult to dissolve in water, or which are not dissolving it in water at all. For example, as I told you, we are working with mainly cerium-based intermetallic compounds. So in this case, we need to find out a suitable solvent. Typically, one of the constituent element is the solvent, which has a low melting point. Like for example, this is in this case, can you see this? We wanted to grow cerium cadmium 6 crystal. Cerium has a melting point around 800 degrees centigrade. Cadmium around 400 to 500 degrees centigrade is the melting point. We use this cadmium in excess quantity because it has the lowest melting point, and we are using that as a solvent to grow the crystal. So to grow this crystal, putting it in cadmium, and cadmium melts at around 400 to 500 degrees centigrade, at least to 500 degrees centigrade to make it liquid. So for that, we cannot use our glass beakers. We are using this sort of alumina crucible. So this is an aluminum oxide crucible. This is called crucible, and this can withstand up to 1600 degrees centigrade. And we are taking the material to be crystallized in this alumina crucible, inside in this alumina crucible in some ratio with large quantities of cadmium.
7 to 93.
Yes, 7 to 93. And then the material is here inside this alumina crucible. We put a small quartz wool here. This quartz wool is necessary to separate the crystal. See, right now, this entire thing will go into your furnace, which is a resistive heating box type furnace, and then we will heat up to 1000 degrees centigrade. So this is not a glass. This is a quartz. Quartz can withstand up to 1400 degrees centigrade in principle. So, but we heat this to 1050 degrees centigrade and maintain this at 1050 degrees centigrade to make a proper homogenized solution. And then we slowly cool down. The principle is exactly the same as that of we have grown for copper sulfate. But only thing is that here we are using elevated temperature.
So it's like you provide enough solvent for the material to dissolve.
Yes.
And after the crystal is formed, you take out the excess.
Exactly.
Solvent.
Exactly. So right now, we after we put this in the furnace, we do this homogenization process, cool down at the rate of 1 or 2 degrees centigrade per hour, depending on the material. So the entire process takes about 20 to 21 days. So this is a long process. So then, before it cools down, we take this crucible from the furnace in the hot stage, around 600 degrees centigrade. We take it out from the furnace, put it upside down in a centrifuge. That means the centrifuge will rotate at a very fast speed at around 1000 RPM. And then the flux, which is in liquid state, the quartz wool will filter the flux, and we can get the crystal, very, very beautiful single crystals out of that. I don't have any right now, any crystals here. The flux grown crystals are not there to show you. But anyway, and the Czochralski method, which you have seen the tetra, those crystals will look like this. You can see a very shiny surface. So this is a cerium rhodium tin to single crystal.
So this entire long thing is a single crystal.
It's a long thing, it's a single crystal.
Okay.
So how do we say that it is a single crystal? That we do X-ray diffraction. So from X-ray diffraction, we can confirm that it is a single crystal or not. So right now, I am going to show you how we do the X-ray diffraction studies on these crystals. So we have an X-ray diffraction facility here. I'm going to take you there. Switch it off. So this is our X-ray diffractometer. Typically, once we grow the crystal, we bring the crystal to find out the orientation of the crystal. So here we are using a molybdenum target. So there is a filament which is there inside, and this is a tungsten filament. We give a small current to the tungsten filament, about 20 milliamperes or 25 milliamperes, and then the tungsten filament emits electrons, and these are accelerated by a very high potential. Very high potential, I mean about 25 to 30 kilovolts. That means from here to here, we are supplying a voltage of about 30,000 potential difference, 30,000 volts. And these,
it's less than a foot.
yes, it's less than a foot, half foot, like a half feet. So you can see that the electrons are accelerated and it hits the molybdenum target here. And then, and this molybdenum target is water cooled. Up to this point, water comes and it is, otherwise the molybdenum will melt just like anything, because the temperature will be very, very high because of this high accelerating potential. And then these X-rays are collimated through this collimator. And this is the X-ray film which we used to record our X-ray diffraction pattern. And we take this sample.
Similar to a photograph.
Yes, yeah. So these, I can show you if you want to see the. No, I'll just. Oh, okay. So I'm going to show you how the X-rays look like. X-rays are not visible to eyes, so you have to put a fluorescent screen. And typically, one should. These are hard X-rays, and one should be very careful with when you are working with the X-ray instruments. So right now we are the entire thing is shielded with the lead sheet. Just for the demonstration, I'm going to turn it on for about few seconds, and then I will switch it off. You can see the spot of this X-ray. So you can see the green color dot. So that's the X-ray that is coming out. You can see that green color dot. So these X-ray falls on the sample. So here you can see that we have a silicon crystal which is kept here. This is a silicon crystal. This is a silicon crystal, and we have a collimator here. This is a silicon crystal. Okay. I think the lens is that.
It's going out of.
So this is the silicon crystal. Yeah, it's okay. It's okay. So now that's the silicon wafer. We can find the orientation of this wafer by doing the X-ray diffraction technique. So you can see that silicon wafer is exposed to X-ray. I think it has been already exposed. We can just see how the X-ray, I mean the diffraction pattern looks like. So you can see the film is the image plate. We call this. It is like this, and then this is the image plate which records your X-ray diffraction pattern, and this can be scanned using our scanner. So there is some special scanner. Yes. Okay.
So can I reuse the film once for my
When the image plate is scanned, it also automatically gets erased. So we can use this, reuse this for about 10,000 times.
Oh.
So right now the image is being scanned, and the scanned image will come to this computer. So this is the same silicon pattern, or okay. So you can So now the image is scanned. You can see the So you can see beautiful Laue diffraction pattern. Each spot here corresponds to a particular crystallographic plane, and we can say the
Dots are what signify.
each spot corresponds to a particular crystallographic plane. So that means there are many planes inside the crystal, and each spot defines as one particular HKL, Miller indices. So from the overall pattern, we can find out whether the crystal is oriented along A axis or along the B axis or along the C axis. And you can see this is some other crystal orientation. This tetragonal. This is a tantalum arsenide single crystal, which is a hexagonal crystal system. It has a particular pattern for this particular space group, and we have grown this crystal in our lab. And since the spots are seen, we can say that this is a single crystal, and this is again another single crystal. Diamond.
I see so many bigger dots and smaller dots. Does it have any?
So depending on the intensity of this particular crystallographic plane which diffracts, so you have different intensities of this one.
And some things are kind of oval, some are
Okay.
circular.
If the spots are spherical, we say that it is a good quality crystal. If that spots are a little bit elongated or ellipsoidal, then we say that there may be some sort of defect in that. So one needs to do some kind of annealing to get rid of this thermal shock and all these things.
So it's important to get a well-defined pattern.
Well-defined circular pattern. That means that indicates a good quality single crystal. So we orient the crystal using this Laue diffraction, and we take the crystal to the cutting machine, and we cut the crystal along the crystallographic direction to study the anisotropic physical properties. So one of the advantages of growing a crystal is to study the anisotropic properties. That means the crystal, if you measure the physical property along different crystallographic directions, the properties are a little bit different. So to study this anisotropy, we need to grow a single crystal. So that's what we are growing in our lab. So as I told you, we are doing anisotropic physical property studies. For that, we are using a specialized instrument, which is called physical property measurement system. So this is a physical property measurement system, which can measure electrical resistivity, heat capacity, thermal conductivity, and all these things. And it can do the measurement from room temperature to 2 Kelvin. So it can we can do the measurement from room temperature 300 Kelvin down to low temperature 2 Kelvin. So this is how the samples are. This is to measure the electrical resistivity. We have 2 different samples along 2 different crystallographic directions. We make 4 probe contacts. The current is passing through the sample and coming out on the other side. And in between, we are measuring the potential difference. That means the voltage. So from this, we can measure the electrical resistance of the sample. Suppose if the sample is superconducting, we can see a 0 resistance. If the sample is having a magnetic ordering, we can see the magnetic transition at some low temperature. So that's fine. So here, these are 2 different instruments. This is again a cryostat, which contains liquid nitrogen and liquid helium. Inside this, we have a superconducting magnet, which can go up to 9 Tesla of magnetic field, 90,000 Gauss. And here we have a 14 Tesla magnet, 140,000 Oersted, 140,000 Gauss of magnetic field is possible in this instrument, and we can go down to 2 Kelvin, and we can do the electrical resistivity measurement on this sample. So these, once we grow the crystal, we cut the crystal along the crystallographic direction, and we bring the crystal here to measure the electrical resistance, heat capacity, thermal conductivity, Hall effect, and these kind of measurements. And this is our liquid helium container. So we get, there is a liquid helium plant in TIFR. So we get liquid helium from our plant, and the liquid helium is transferred to these 2 cryostats using a transfer tube. And most of the helium, it again goes back to our low temperature facility. So that means we are not wasting any helium. The helium which boils off is again sent back to our low temperature facility. It is liquefied, and we are reusing that helium gas again and again for our measurement system. So is that ready? Then we can do the second melting of this alloy. So right now it is at vacuum. You can see.
Camera. We need a camera.
So is it back in action? So right now we pumped it again. We flipped this upside down.
He's connected to this lab. Audio is audio.
Yeah. Okay. So we have melted it once, and we have flipped it upside down. You can see from inside using this one. You can see that the sample is flipped upside down. There is some technical issue. Is it live? Okay. So right now we have flipped upside down this alloy. We are going to melt it again to show you how it becomes a homogeneous alloy. So right now we have to put this cover. So we are melting it for the second time. And the melting point of this sample is quite high. So you can see that all the three metals are mixing homogeneously. It's okay. So now the alloy is getting homogenized by melting repeatedly. So I'm rotating the heart so that to make sure that the button melts. Looks like the melting point of this sample is quite high, so we need to supply more current. All right. So right now, this has become a completely molten solution, but we have to melt it some 2-3 times more before we start the crystal growth of this sample. So you can see that the bellow is bending like this. That is because it has gone above the atmospheric pressure. Because of this huge amount of heat inside, it's quite high. So now once I switch off the thing, the below has become a normal shape because again the pressure inside has become close to atmospheric pressure. So these are the various crystal growth techniques that we adopt in our lab to grow crystals. And our interest is to study on the magnetic and superconducting properties of various metals and alloys. So particularly our interest is on rare earth-based intermetallic compounds, where we see these rare earth-based compounds show magnetic ordering down at low temperatures, and we are extensively studying these kind of materials these days. So right now, if there are any questions on the YouTube, or I can just take up some questions. So right now, you can see that the growth is again happening. Right now, you can see that this is how we have engaged this feed and seed rods, and you can see that the pulling speed is about 0.3 mm per hour. So the growth is a very slow growth rate for this sample. So in 1 hour, it will grow 0.3 mm. That's the pulling speed that we employ to grow this system.
That's it. In 1 hour,
0.3
0.3
mm.
millimeter.
It's a very, very slow growth process.
And how does one get this slow speed?
So there is a stepper motor inside, and it can control the speed actually. So this is how you can see from inside. This is how it looks like. So there is a top stepper mode is there. The stepper motor is there. That has, and we have a at the bottom also similar kind of. You can see that there is a valve there that is to pump out the gas, and then we close this valve, and we can put any gas inside, either oxygen or argon plus oxygen. Those kind of mixtures can also be put. And the top one is the feed rod moving mechanism.
So Tamilvel, there is one question on YouTube,
yes,
which says, why do we need X-rays to check if something is a single crystal?
See, because the wavelength of X-rays is comparable to the lattice constant of these materials. So if you are using a white light wavelength is huge and it cannot diffract. So if you want to have a diffraction pattern, you need to have a wavelength which is comparable to the lattice constant.
So the wavelength of the X-ray is similar to the spacing between the atoms in these crystals.
Yes.
And hence it allows us to take a sort of picture which tells us where are the crystals,
where
the
atomic
atoms
arrangement.
located in the
Yes,
crystal.
yes.
So that's why we use X-ray.
Yes, yes.
Okay, let me check if there are any other questions. Yes, right. Okay, remember that if you have questions after watching this, for those who are watching it later, please feel free to put your questions in the chat box. We will try and send these questions to Professor Tamilvel, and he will be able to answer them, and we will put the answers in the YouTube chat as well. So thank you very much for showing us many different types of crystal growth, starting from very simple solution growth of copper sulfate crystals to how one melts the oxide crystals and how one uses the electric arc to melt various metals. And then we also saw how we used a Laue diffraction technique to look at whether the crystal is the crystallinity of this material that we've grown, and then another measurement system to look at magnetic and electric properties at very low temperatures. So thank you very much for this very nice live lab tour where we actually melted things not once but twice and got to see it. So thanks a lot, and please keep watching Chai and Why. Remember, if there's a fifth Sunday, we are from the lab in TIFR, a live tour. On that note, thanks a lot for watching, and have a good evening.
Thank you. Thank you. Thank you very much.